Let's get started. All right, so a little bit of recap. The big difference between a position time graph and a velocity time graph is that a position time graph describes where the object is at a given point in time. It doesn't tell us anything about, or doesn't directly tell us anything about how fast it's going or how it's going to change its motion in any way. It just tells us, I'm right here at this point in time, and we'll be somewhere else at some later point in time. Okay. So to start off with, let's do a little bit of review. I want you guys to picture or describe, chat out in the, or type it out in the chat. How is this object moving as time goes on? What is it doing? And if you can think of a real life example that might explain this sort of thing, go ahead and share that one out too. All right, so a couple things we can say about this object. Number one, it starts pretty close to the origin. So it starts at our 0 point. It's not starting far away from our imaginary camera or sensor or whatever we're doing to actually record this data, but it's starting roughly at the 0 point. It then moves away and about somewhere around 2.5 seconds reaches its farthest point away. So this object has moved away from us, and between 2.5 and 4.5 seconds, now it's coming back to where it started. At 4.5 seconds, it's back to where it started. And now as it continues on, it now goes behind our starting position. So we started going in a positive X direction. We came back to the origin, back to 0, and now we're in the negative X direction. Somewhere between 4.5 to 6.5 seconds, we're moving away behind our starting position. And then somewhere around 6.5 seconds, it turns around and starts coming back and ends up at 8 seconds being right around the 0 point, right around where it left its spot. Here, we can show it with a laser, that'll work. So basically between this stretch from like 0.5 second to 2.5 seconds, we're moving away from our origin. 2.5 seconds down to 4.5 seconds, we're moving back to the origin. Then 5.5 to 6.5, again, moving backwards. So we're going in the same velocities we were before in the backwards direction, so negative velocity there. And then we end up coming back to the beginning here. Some possible examples of this. This curve shape is very, very, very typical of what you would see for a ball being thrown in the air. So I toss a ball up, it goes away, hits its highest point, then comes back. This part right here could be the same sort of motion, except for, so let's say I'm throwing a ball up, I miss the catch, so it falls below where we started and then back up again, possibly. Or this could be somebody walking forwards, then backwards, and then back to where you started again. That's a possibility too. It really depends on the context of the question. But this general graph could describe many different types of motion. Also, notice that this is just saying position. If we were to get this on an exam question or something like that, they would give a little bit more background as to, is this vertical motion? Is this horizontal motion? Is this some sort of combination of the two? It really depends on what the question is going to say. But for a generic position, this could be, again, walking forward, stopping, turning around, going back to where you started, going behind where you started, back, and then forwards. Okay. And again, for those new people who just jumped in, if this is something I'm going too fast, you're confused, just shout something down in the chat. I will definitely stop and come back and hit this again. Okay. So that's our position versus time graph. Let's say now I want to find velocity from this. Well, our basic definition of velocity, which hopefully we've covered before, but if not, just in case, velocity is telling us how our position changes over time. And just like we can have positive positions in front of our starting point and negative positions behind our starting point, we can end up with positive velocities and negative velocities. Positive velocity means we're moving in the positive X direction. I'm going to refer to that as being moving forwards. Again, depending on the question, that could be moving up and down, depending on our relationship and our axis choice. Negative velocity is moving the opposite direction. So it's going backwards in there. So if I jump back to our, how is this object moving? I would say from like 0.5 seconds onwards to 2.5 seconds, we end up with a positive velocity. We are moving away from our starting point. From 2.5 seconds down to 4.5 seconds, we have a negative velocity. We're moving backwards or back towards our starting point. Actually, we can say from 2.5 all the way down to 6.5 seconds, we are moving away or moving backwards in our motion. We started walking away till 2.5. Now we're walking backwards, and we keep walking backwards till about 6.5 seconds. That's all negative velocity going on there. And then finally, from 6.5 seconds to 8.5 seconds, we now have a positive velocity again. We are moving back towards the starting point in that positive x direction. Okay? Now, some of you may be saying, well, wait a minute, don't we stop in the middle here? And yeah, we do. We do hit this sort of zero-ish. This almost looks like it flattens out. So we probably should say we had negative, hit zero, and then went negative again. There. Okay. So the math behind this, I'm sure you guys have seen something similar. Positive velocity is always the upwards direction. What? Okay. So positive velocity typically will be, ignore what type. Okay. So the cool thing about this is you can choose which direction positive and negative is. Conventionally, we're going to choose positive y to be up and positive x to be forwards. But sometimes, depending on the question, we may be better served by just talking about everything down being positive. Let's say I'm just dropping a ball, and I'm never going to have this ball go upwards. I may, when I frame the question, just declare on the paper in my mind that everything is going to be down and positive in there. For this sort of stuff we're doing right now, I'm always going to say positive is either up or to the right, I guess. If you're thinking about a graph or an axis graph, saying up and to the right would be my positive directions. And then therefore backwards and to the left, down and to the left would be my negative directions. But that can all be switched depending on personal preference and what you want to do with a given question. But conventionally, just like a XY axis coordinate table, up is positive, right is positive, and then down and left are negative directions. Okay. So hopefully the equation on the board isn't something brand new, but if it is, this is basically the math representation of velocity. Velocity is delta x. Delta, Greek letter, means change. So this is the change in x, or the change in my position over the change in time. X is used when we're talking about horizontal motion. If you were doing vertical motion, we just swap that out with a y. So v horizontally would be delta x over delta t. Vertical will be delta y over delta t. Okay? And all I really did here was I just did a little cross multiplication, solved it for delta x. So I have delta x equals v delta t. And now this is actually the key to making a velocity time graph. Realizing that this particular arrangement, this delta x equals v delta t, is a equation of something. And it's not just an equation for velocity, but it's actually a mathematical equation that you have probably seen in one of your algebra classes, or maybe if you did geometry or something like that, you may see it there as well. Take a second and see if you can figure out, what is this equation, this delta x equals v delta t, what is that similar to? All right, so let's see how we did. Hopefully, you guys realized that this is really just the equation of a line. Delta x equals v delta t is exactly the same thing as y equals mx, and then b would be a zero term there. So if we make this graph with delta x, the change in position on the y-axis, delta t, the change in time on the x-axis, that means the slope of this graph must be the velocity. So to help us out and understand this a little bit more, I'm going to throw a button up. I think this will work. Hey, is that button up? Hopefully. This button will take us to a Desmos simulation where we're going to mess around a little bit with velocities, times, slopes, and stuff like that. See if we can figure out how this works. So give me a second. I'm going to switch the screen over to Desmos, and we'll go from there. So I'll share tab, this one. All right, so hopefully this is all loaded now. I can hope. Let's see. It's taking a sweet time to load. Okay, so we have stuff going on here. So take that away, take that away. And this did not save the full thing. That's awesome. Okay, so what we've got here, let's assume we have a simple straight line with a slope of 1. So we're going to make it just a 1. Okay, so we're going to start off with a basic line. And this is our basic distance time graph. So this basically says that every second my distance goes up. Well, it looks like about 5. So let's make it exactly 5 for the ease of math here. Exactly 5. Let me zoom in a bit. Okay, so every second our distance increases by 5. So 1 second we have gone 5 meters, 2 seconds we have gone 10 meters, etc., etc., etc. Basic constant velocity sort of motion. This graph then is a straight line. It's linear. And this is what I would expect from a distance time graph where the velocity is constant. Now, if you ask me to find that velocity, well, we can do a couple ways. We can just say that every 1 second, the velocity goes up by 5. We have found the slope of that line to be 5. And now let's see if I turn on the velocity graph. There it is. That green line is the graph of velocity of this object. And it is a constant 5 meters per second because the slope of that red line is a constant 5. It doesn't change. It's a constant velocity motion. I would expect my distance graph to be linear and my velocity graph to be just a horizontal constant value. All right. What if we do something a little bit crazier? What if I make my position graph not move at all? Well, this one, position graph, red line again, completely horizontal. What does that mean? It means that as time goes on, I don't change where I am. The ball is just sitting there. The car doesn't move, et cetera, et cetera. And this means that my velocity should be 0. So again, we'll turn on the velocity graph and we see it right down here at this 0 mark, that the velocity is constant and 0 the whole time through. So we can look at this and say horizontal red line, slope of a horizontal line is 0. That means that my velocity should be 0. Oops, let's make this a whole number now. I can make this go as a whole number. Linear graph of position means a constant horizontal line again, but now not at 0, at some other number. So in this case, my slope is positive. It's a positive 5. If I made my slope a negative 5, now we see this whole thing kind of flip around, and now I'm going backwards 5 meters every second. So my velocity is a negative 5 as well. So if you look at a distance time graph, you can look at the slope of that graph and figure out the velocity at that point or over that range of seconds in there. Okay, so let's do a little, or I should ask, does that make sense? Okay, so I got yes in the chat. So now let's do a slightly more difficult example here. Let me make this not a nice linear graph, but let me make this go back to positive here. Let me make this a squared graph. Okay, so now if I have the red graph being squared, well, now we got something a little bit different here because the slope of this red graph is still positive, but it's positive and it's changing. It's not a constant value anymore. It just keeps going up and up and up. In the first second, I go 5 meters. In the second, I go 20 meters. In the third second, I'm up to, oh, wow, big number. We're up to 45 in there. That is not a nice constant pattern. And that tells me that my velocity graph cannot be a nice constant value. It's got to be changing. So how would I go about solving this one? Well, what I would do first is find the slope between the first second. So 0 to 5, my slope is 5. In the second, I go from 0 to 20. 0 to 20 divided by 2, that slope is 10. In the third one, 0 to 45 in 3 seconds, my slope is now 15. And I would start plotting those values. I would plot a 5, a 10, a 15. And hopefully, if I click the right thing, I run the wrong screen, I get a linear relationship so that I've got 10, 20, 30. Apparently my math was off here. For that, oh, that's right. Just look at, so I went 10, 5 to 20 in 1 second. That's why the 15 was there. So we just keep going up. This one gives me a linear graph for my velocity. Linear velocity, not horizontal. Changing velocity, this is when we have acceleration going on. So if I look at the red graph and see that it's curved, I know we're accelerating. I know my velocity needs to change. If I look at the red graph and see, oh, it's linear, I know my velocity is constant and we are not going to accelerate at all during that motion. Okay. The other cool thing we can do with this is we can go backwards. So I'm going to turn off the function or the velocity graph, the position graph right now, and I'm going to turn on this little handy feature. Okay. For a velocity graph, which again is our purple line, what we can do here is we can use this to go backwards and figure out how far we have traveled in a given amount of time. So to do that, we're going to look at the area under this curve. Now, if we did some calculus, or if you're thinking about taking calculus in the future, the term for this would be the integral. But calculus doesn't come into AP1, so we're just going to use the term the area under the graph. So I will look at my graph, and then I will look at everything from the y-axis to that value. So it can be either going up, and we would call that a positive area, or if my graph suddenly becomes below this chunk right here, would be a negative area. And I just have to change my signs on this because that was only for positive. So if I spin this around, we would end up with a negative area there as well. On a velocity time graph, this area represents the distance that you have traveled. So just like we had, let's see, undo. There we go. Undo one more time. Okay, so just like we said, our function graph at 2 seconds went 20 meters or 20 centimeters or whatever units we're using here. The area of this triangle tells me the same thing. Okay, area of a triangle, 1/2 base times height. So 1/2 of 20 times 2 is 20. And that gives me the distance that I have traveled in there, which is pretty cool that I can take this crazy curve of a position graph and represent the same thing by the area under this nice straight line. Now, commonly on an AP exam, if they're going to ask you to do this, it will be for a velocity time graph. This could also be done with an acceleration time graph, and that will give you the velocity and stuff like that. But that is much less common. More often than not, you're going to see this with here's a velocity time graph, and then we do what's the position from it. So that being said, if there's any questions about this sort of relationship, we're going to move on and do a little constructing a graph from some AP questions next. But if there's any questions on how the slope of a distance time graph gives you velocity and the area of a velocity time graph gives you position, you can ask them now, and I will do my best to answer them as best I can. So we're back to this. So big idea, again, is that if you have a position time graph, velocity and time, we're going to have the slope of that graph be a velocity one. Okay. Click down. Okay. So, for example, we have a very basic distance time graph, and we were trying to figure out the velocity of it. So the first thing I would do when I look at a question like this is, number one, make sure you know what the axes are. Common mistake my students make is they will look at any graph and then assume it's some kind of it. So this is a displacement or a distance time graph or an x versus t graph. Any of those terms are fairly interchangeable. Look carefully at those. Look at the units, look at the scales before we try to jump into doing something with it. Let's make sure we understand what this graph is saying first. So when I look at this graph, I notice a couple things. I'm going to say the slope of this looks constant and it looks negative. And that's about all I can say here. It starts off at 5, negative slope, ends up at -4, and somewhere around 27-ish seconds, we cross 0, which means we started in front of our imaginary camera, our imaginary 0 line. We walk backwards towards it at a constant speed because this slope is constant. And then, sorry, I should start the presentation again. Then we go from there. Yeah, there we go. So now I got my pointer. So because this line is a constant slope, I would expect a constant speed walking backwards. We then walk backwards behind where we started, and we just keep walking. We are going to end up behind our 0 point, and that's okay. So now if the question says, let's do some math, let's calculate the slope of this. Well, the nice part is we can really do this at pretty much any point you want to on the graph. I tell my kids, let's not worry about trying to guess the points on here. Like this point right here, this 10 seconds and 3 and maybe 3.1, 3.2, don't guess those. Pick the nice easy points. Pick the, oh, this looks like it hit -4 and this is 50 seconds. Or maybe this 0 point works, that this looks like it's 27.5, halfway in between, and this took 5 meters. Something like that is where you're going to want to pick your points from. We don't want to pick it from other random things or other tough points to guess from. Always pick the easy ones. Okay, so I want to find the slope. The slope of this line, change in y over change in x. Or in this case, change in displacement over change in time. So I ended up at -4. I started at 5, so -4 minus 5 gives me -9. And this took, well, I ended at 50 seconds. I started at 0 seconds, so this took a total of 50 seconds in there. That being said, we take -9 divided by 50, and we get a -0.18, about a -0.2 meters per second. So pause for a second. Does this seem reasonable? Not is it right or not, but does this make sense in our minds? All right, so hopefully you're seeing things like, yeah, that kind of makes sense. The slope is negative because our graph definitely has a negative slope here. If we ended up with a positive slope, obviously we made some major mistake in the math or missed a minus sign somewhere on the line, something like that. Also, this 0.18 seems pretty small, but that kind of makes sense. We took about 50 seconds to walk almost 10 meters, which means we should take about 5 seconds to walk 1 meter, and that 0.18 is pretty close. It's in that ballpark. So this seems to be a reasonable answer, whether or not the math is absolutely correct. It at least fits our conception for what we're going to do on this question. Okay. All right, so next thing, it's your turn. Take a look at this graph. This is the same one we talked about earlier when we were talking about the position. And let's take a minute or two. What time intervals does this object have a positive velocity? All right, so right around 2 seconds. Yeah, that definitely has a positive velocity. If I was looking at the slope of this line going up here, that still has a positive looking slope to it. It's still trending upwards in that positive direction. Okay. You actually probably could have said anything between like ½ second or position 1 all the way up to this very highest point right here. This highest point is when you turn around, and that wouldn't be positive anymore. So I would say anywhere in this general region would be a positive velocity. The other place to look, though, would be in this chunk down here. Starting right around 6.5 seconds, we start sloping upwards. We get another positive slope on our graph, which means we have another positive velocity going on there. Okay. The other chunks, well, anytime you see a top of a hill, so this point right here, 2.5 seconds, you stop. The slope of that would be 0. It's a tangent, or that line right on top of the curve there would be 0. So this is the stopping point. This is when you would stop going forwards and start moving backwards. Go from a positive velocity from 0.5 second to 2.5 seconds to a negative velocity from, let's say, 2.5 down to 4 again. So this point right here would be a 0. Anything before that, I would say, is positive. And then same thing down here between the 6.5 and 7. The 6.5 point is a 0. You've gone from a negative slope to a positive slope. So you're going from going backwards to walking forwards. And I would say that is a 0 point right there. And then positive slope anywhere from 7 or 6.5 all the way up to 8, maybe even 8.5 on there too. So basically for this, you're looking at any time your graph is making a positive slope, going up in a general y equals x sort of direction, you have a positive velocity. Anywhere your graph is going down in a y equals negative x sort of direction, you have a negative velocity. Okay? And anytime you have the top of a hill, either positive, or the bottom of a hill, bottom of a trough, bottom of a hill, however you want to describe that, in the negative side, those are 0 points where you stop moving. So let's take a look at another one. This one came right out of an old AP practice exam. So they're talking about car X and car Y. Car X starts off moving at a certain speed, V naught, and car Y starts off stationary. And then as time goes on, car X maintains its constant speed, and car Y starts to travel upwards, increasing its velocity more and more and more. Okay. So the question asked us something like, how far did car X go in 20 seconds? Okay. And then how far did car Y go in 20 seconds? So we'll start with car X because that's a little bit easier one to do. Car X starts off with a constant velocity, perfectly horizontal, does not change. So that never changes from its V naught original value. So if we're doing the math here for car X, well, we can use our basic kinematics equation. This is the x equals x naught plus V naught t plus 1/2 at squared equation. Car X doesn't accelerate. Its velocity stays the same. So that simplifies down to just V naught times t, or the velocity there was times the time. Now, in this case, if we're looking at 20 seconds, it would just be 20 times the velocity we started at. But the cool thing here is if we go back to the graph, this rectangle up from 20 over to 0 has the same area as our answer. This again is showing that a velocity time graph, if you look at the area underneath the curve, you get the distance that the object has traveled. So in this case for the car, I would do, well, we're looking at length times width. So my length would be 20, my width would be V naught. So I would still get 20 V naught in there. It's the area under the curve. Okay. So let's go back for a second. And why don't you guys try to apply that same concept to car Y? How far does car Y travel in, let's say, the first 20 seconds? So my first step would be, okay, so I'm looking at car Y going up, and this one happens to be linear, not horizontal at all. But if I go down to the 20 seconds, this makes a very nice triangle. And the area under the curve, the area I need to worry about is this chunk right under here. So let's recall, or I'm pretty sure this is on your reference tables for the exam too. I don't think this is a memorize it, but if you memorize it, more power to you. That's a better concept. Area of a triangle is 1/2 base times height. So for car Y, my base is 20 and my height is V naught. So for car Y, it would be 1/2 of 20 times V naught, or 10 V naught. So what that means is at this point, at this 20-second point, car X has gone 20 times its speed, and car Y has only gone 10 times its speed in terms of distance. Now, at this point, this is where I'd ask my kids, does this make sense? Does it make sense that car X has gone farther than car Y? And hopefully, this does make sense. Hopefully we say, well, car X has always been faster than car Y, except for that 20th second. So if you're running against somebody who's always faster than you, sure, they're going to go farther than you are. Car X should go farther than car Y. It might also help to say something like car Y's average speed starts at 0, ends at V naught, is half of that. So it should make sense that car Y goes half as far as car X does in that given amount of time. So car X, we did the area under the curve, this rectangle. It was bigger than car Y's, so of course it should be farther along than car Y, both graphically, or if you want to do it mathematically, that works too. Just using your kinematics equations, the x equals x naught plus v naught t, and then average velocity is the initial plus the final over 2. Either way works for that. Okay. So this is kind of our application question. How do we know when the cars have traveled the same distance? What on the graph would have to be the same to tell us that these cars moved the same exact distance throughout this motion? What we know what happens when the cars have traveled the same distance, the areas will be equal. So the area under car Y's graph, example, this triangle, will be equal to the area under car X's graph. For this example, it happens at 40 seconds. They both will have the exact same area under the curve. If they didn't, then they would not have traveled the same distance. But for this example, right at 40 seconds is where they would have the exact same area and they would have the same distance or same displacement traveled. So let me do a little summary time here. This talk focused on velocity and time, but this also applies to acceleration time too. So this is the table that I have my AP kids memorize because it gives them the clues for what each graph tells us. If I have a position versus time graph, I can find the slope of that to know what the velocity is. The area on a position time graph really doesn't give me anything useful. It's position times time, which nothing physically significant about that. For a velocity time graph, this is the big one for today. We get the slope of a velocity time graph tells us acceleration. The area tells us the position. And if we had an acceleration graph, which we're not covering in this talk, but just to include it on the table, the acceleration versus time graph gives us the change in acceleration over time. The term for this is jerk. It's used in engineering, or if you take APC in the future, that's where that would come in. Not used in AP1, but extra information. But just like the area of a velocity time graph gave us position, the area of an acceleration graph gives us velocity. So you can think about it. The slope goes from position to velocity to acceleration. If I have the position graph, it gives me velocity. If I have the velocity graph, it gives me acceleration. The area goes the opposite way. If I start with acceleration, it gives me velocity. And if I start with velocity, it gives me position, slopes, and areas on there. And if we end up with something from that, that's wonderful. Okay. So at this point in time, it's practice time for you guys. So we're going to run through a couple more AP style exam questions. Again, these came off of either old AP exams or the practice exams or the publicly available stuff in here. This one was the first part of a free response question. This was probably a 7-minute free response question. But we're going to take as much time as you guys need for it. So they give us the vertical position of an elevator as a function of time. So they say this is where the elevator is as a function of time. And what we're supposed to do is graph the velocity of the elevator as a function of time. All right. So to do that, let's first take a look at this graph. Number one, it's a position versus time graph. So I'm going to jump back to my table here quickly. It's a position versus time graph. That means that if I can find the slope, it tells me the average velocity, which is great because that's exactly what the graph or the question is going to ask me to do, graph the velocity as a function of time. So if I look at this, there are 3 big areas on this graph that have a constant slope. From 0 to 8 seconds, from 10 to 18 seconds, and from 20 to 25 seconds. All those have a nice constant slope going on, which means we can do basic slope equations. Y equals mx plus b, or slope is change in y over change in x, or y2 minus y1 over x2 minus x1, depending on how your algebra teacher taught you. That's what we're looking at to find the slopes. Okay, so I'm going to chunk this up into 3 parts. The blue slope looks positive and constant. The red slope looks horizontal. That should be a 0. And the yellow slope looks negative and constant. So first things first, let's do the blue slope section. Okay, so I'm going to do some math out. The slope for this, change in y over change in x. Again, you could pick any point you want to on that section because it looks pretty constant. I'm going to choose the nice one that has the crosshairs nicely on it. In my case, it's 12 and 8. 6 and 4 also looks really good as another point you could do. Would give you the same exact slope. So in this case, the slope for the blue section, delta y over delta x, 12 meters over 8 seconds to get 1.5 meters per second. Okay, so we can graph that on our velocity graph here. 8 seconds up, we are constant 1.5 meters per second. So horizontal line on that velocity graph because the slope for the blue section did not change all the way throughout that time. So no changing slope on the distance graph means nice horizontal line on our velocity graph. All right, second chunk. Well, this one's pretty easy. It's a horizontal line. A horizontal line has no change in y, so its slope is automatically 0. And I don't really have to do any math for that. I can just say, hey, that slope is 0. And it's a 0 between 10 and 18 seconds. So my graph looks something like this so far. We've done the first chunk, found the slope. We did the second chunk. It was 0, so we just filled that in there. And then finally, for the yellow chunk, again, looks like it's a constant slope from about 20 down to 25 seconds. I'm going to pick points that match up nicely. The only one that really looked nice to me was doing that 12 and then the 0 on there. You might have been able to figure out something else depending on how well you were good at guessing, like, was this exactly halfway in or not? But for me, again, take the easy points. Take the ones where the crosshairs go over it nice and easy so we don't make a mistake on that part. So in this case, This slope is negative, going down. I started at 12, I ended at 0. So my delta y would be negative 12. This took 5 seconds. So we get a negative 2.4 meters per second for our velocity. And again, that slope looks pretty constant, which means on my graph, we should have a constantly negative point here. And so negative, so we're in the negative range, constant, and that's about where 2.4 goes. If you were off a little bit, you get partial credit at least, but they're going to give you a little bit of leeway as long as you're not obviously 2.5 or 2.2 or whatever, stuff like that. So far, so good. That's kind of what our graph looks like so far. The only problem here is we are missing some sections. We are missing the chunk between 8 and 10 seconds, and we are missing the chunk between 18 and 20 seconds. So the question is, how do we fill those in? Well, we look at this, and I'm going to look at each one fairly similar. This slope goes from being positive to being 0. Okay, so my slopes that start positive, the 1.5 we found over here, and then slowly curve until it's 0. And the same sort of thing here. This slope starts at 0 and then curves again towards the negative. Both of these things, both these curves are concave down, which means we should end up with a decreasing velocity. So in this case, we're just going to kind of go through and we kind of wing it. So my slope starts off here and then it curves down to 0. And then we're at 0. And then we curve down to the 20 range on that. If that slope, if you did this with a straight line, my guess is you might lose a point on this. But typically the scoring guide for a question like this is much more concerned about the blue, red, and yellow sections and much less concerned about how you connected them. Was it exactly a straight line or was it a curved line on there? With that. But this is the way, this is the actual key, and that's what it would show, is those curved lines going through there because your speed does change and curve there in a non-linear fashion. All right. Then this question went on to ask about doing something with projectile motion afterwards, which is out of the realm of this talk. So we're going to move on to a second one. But before we do, are there any questions about how we went about solving this question? Okay. So next one. This one obviously is multiple choice right off the AP practice exam. So this says that the object's velocity as a function of time is given in the graph above. Which of the following statements is true about the motion of the object? So how is this object moving? Okay, so number one, we see a graph. The first thing we do is figure out what kind of graph this is. So in this case, this graph is a velocity versus time. It is not telling you position. It is telling you velocities. So looking at this, saying that from 4 seconds to 10 seconds, hey, that's horizontal. Horizontal on a graph doesn't mean it's not moving. If this was a distance graph, absolutely, that would be not moving. But velocity graph, this tells me we're moving at 10 meters per second. So A, not right, simply because the wrong type of graph. Okay. For part B, the initial and final positions are the same. This one's a little bit trickier because, well, we do go forwards. We have a positive velocity for the first 14 seconds. Then we get a negative velocity for an extended period of time afterwards. And that might mean that our areas are equal. So this is one where we'd want to go through and either do the math out, find the area of this trapezoid or the area of this trapezoid, and then compare them. If they are equal to each other, then we do start and end in the same spot. Okay. But this works out to be not true either. So the areas don't work out to be equal. Okay. Part C, the object is slowing down from 14 to 16 seconds. Okay, so this chunk right in here from 14 to 16 seconds, the object is slowing down. In this case, we're not. We were at 0 seconds, or sorry, 0 meters per second right at 14. We had stopped. There is no motion going on right here. And then 2 seconds later, we are moving. We're moving backwards, but we're still moving. We're no longer slowing down. We're actually speeding up in the negative x direction. Okay. So what that boils down to is that we are looking at d, the acceleration. We look at the slopes and how does this slope compare to this slope? And they are not the same value in this case. They are slightly off. So D would be the right answer according to the scoring guide. And that's how you pretty much would tackle this. So first off, A, not the right type of graph. Horizontal does not mean stopped on a velocity graph. Initial and final positions are the same. Check the areas. If the area of this shape down here is the same as this one, okay. If it's not, then they're not stopped and starting at the same spot. Slowing down here, just because we're going negative doesn't mean we're slowing down. We're actually speeding up here because we want 0 to -5. And then accelerations, look at the slopes of the graph. And if they are the same, then D's wrong. If they're different, then they're different. Okay. And here's the last one that we're going to work through. Oops, I was going to skip that one. That's right. We are skipping that question because I didn't put the graphs on it. We're doing some reasoning questions instead with this. The car one previously was the same basic thing as the X and Y car Y thing we did before. But for this one is something you might get as kind of a practice question. The AP exam doesn't throw that on for a ton, but it's also one that you might see like a typical question would be like student A says that such and such is the biggest. And student B says, well, I think this one's the biggest. Which one do you agree with? So that's where this sort of question comes into play, where we have a bunch of different examples, rank them, and then we'll have to explain why A is the biggest or B is the biggest, stuff like that. Okay? So in this case, we have 6 different velocity time graphs, and they all have the same time and velocity scale. So all the velocity blocks going up have the same scale, and all the time ones going along have the same scale as well. We're supposed to figure out which ones have the biggest, the second biggest, the third biggest, the fourth biggest, et cetera, displacements. So which object, A through F, traveled the farthest, the second farthest, the third farthest, so on and so forth. All right, so to do this, we're going to remember that we're looking at a velocity graph. We need to look at the area under the curve here. So in this case, A's has gone 1, 2, 3, 4, 5 blocks. So the area there would be 5 blocks worth of distance. D's, yeah, this is bigger. This is 1.5 plus 1.5 plus 1.5 plus 1.5 plus 1.5. More blocks than A's. So D having more area underneath the curve, more area under the graph than A does. D has gone farther than A. B doesn't look like it's got more area under there than D does. So I'm still thinking D is going first. C just looks like it's the same thing as B, just flipped over. F doesn't go as high for the velocity, and E has some positive negative thing going on here. So D should be our first choice. It is the most area under the curve. It has gone the farthest. Second, probably going to be A, because A has gone 5 blocks. I don't think I can get 5 blocks of area under B or C or F. So I'm going to say A is second. B and C look like they have the same number of blocks in them. And if all we're looking for is the magnitude or the amount of the distance, positive and negative doesn't matter here. So B's positive distance versus C's negative distance will have the same amount, just in different directions. So we can say B and C will have the same thing, and they come in third. F gets 4th place, simply because it is almost as much as B and C, but it just doesn't go as high. And port E is last because this is negative distance and this is positive distance. Those two areas cancel each other out completely, and port E hasn't gone anywhere at all. It is completely stationary, started and ended in the same spot. So D went the farthest because it had the most area under the graph. A, the second farthest, because it had the second most area under the graph. B and C tied for third because their areas were third most. F gets fourth because it's fourth most, and E gets fifth because it is the least distance under all those things. All right, so again, just to recap, major ideas from this stream: the slope and the area of different graphs give us different important information. For the velocity graph in particular, this one super useful because the slope tells you the acceleration and the area tells you the distance or the displacement that you have traveled with that. So keep that in mind, and I hope you guys have a wonderful time.